Welcome to Math 30-2, where we are in Chapter 7, studying logarithms. Now, to begin with today, we're going to look at a few warm-up review questions, and then we'll get into some laws of logarithms and see how we can make use of them in a variety of questions. So here you see a few of the warm-up questions. 1, 2, 3, and 5. I don't know what happened to 4, but do these 4 questions, and when you're done, you can restart the video. So pause the video now and restart once you finish these 3, 4 questions. Well, as we begin here, we are reviewing how to rewrite an exponential equation in logarithmic form. And you'll remember that in our power here, my base is a, so I'm going to write a logarithm with a base of a. And we remember that a logarithm is an exponent, so the logarithm is equal to that exponent of 0, and it operates on the power. The power is equal to 1, so we'd say the log base a of 1 is equal to 0. For number 2, again, on the left side we have the power, and so I can rewrite the log with the base of a. It's equal to the exponent of 1, and it's operating on this a. And then for number 3, again, we'll have a log with a base of a. It's equal to the exponent, which is y, operating on the x. So you'll remember from this that what a logarithm says is, as I look at number 2 here, if I was to rewrite this a as a power with a base of a, the logarithm tells me the exponent. Well, this a is already a power base a, where the exponent is 1, and so that's why the logarithm is equal to 1. Here we're saying if I was to rewrite this x as a power with a base of a, it says the exponent would be y. Well, that's what the exponential equation says up here, where if I rewrite this x as a power with a base of a, the exponent is y, and that exponent is the value of the logarithm. As we look at the next question, here we want to remember from chapter 6 as we look at exponential equations. Here, if I have a base of 2 compared to the base of 10, the base of 10 is going to grow much more quickly. So an exponential equation as we go from left to right will be increasing as long as our base is bigger than 1. So this 10 is going to grow more quickly, so that's going to be graph A, and graph B will be the exponential equation where the base is 2. And then, as we look at the logarithms, we learn that a logarithm and an exponential equation, they're inverses, they're reflections in a diagonal line here, y equals x. And so the graph B will correspond to the graph C. Graph B increases more slowly. Graph C here increases more quickly, but you can see they're mirror images, they're reflections in that dotted line. So B and C will have the same base. Since graph B had a base of 2, graph C will also have a base of 2, which leaves us with graph D, which will have the base of 10, corresponding to this exponential equation where the base was 10. As we look at the next few questions, we are wanting to make some observations. Comparing question 6 with question 7, we can see that we have a log base 2 in both of the questions, and we have a 16 and an 8 in both of the questions. And we want to evaluate these without a calculator just to review the meaning of the logarithm. So since I have a base 2 here, I want to rewrite each of these numbers as powers base 2. So I can rewrite this as log base 2 of 2 to the 4th, that's 16, times 2 cubed, that's the 8. Well, when I'm multiplying powers, I can add these exponents together. Remember, the exponent tells me how many 2's I have repeated as factors. So here I have 4 2's, 3 more 2's, gives me a total of 7 2's. So I have log base 2 of 2 to the exponent 7. And again, what a logarithm tells me is if I was to rewrite this argument, whatever we're taking the logarithm of, as a power base 2, the value of the logarithm is the value of the exponent. So it's equal to 7. Question number 7. We've already figured out that 16 is 2 to the 4th, and 8 is 2 cubed. And so as we did in the previous question, log base 2 of 2 to the 4th is equal to the exponent, which is 4. Log base 2 of 2 cubed is equal to the exponent, which is 3. 4 plus 3 equals 7. And we see that these two expressions in number 6 and 7 give us the exact same answer. In other words, they are equivalent. Why does that happen? Well, you will remember, hopefully, that a logarithm operates on a power. So here I have two powers being multiplied together. And since I have a log base 2, I'm imagining these two numbers being powers with a base of 2. When I have powers with a base of 2 that are multiplied, I add the exponents. Well, you'll remember over here, the logarithm is an exponent. So I'm taking this first exponent and I'm adding it to the second exponent. And I get the same result as when I multiply these two powers. Multiplying powers is the same as adding the exponents. So that's how these two logarithms are related to the laws for exponents. Number 8 and 9, we have a similar situation, but this time with number 8, we're dividing instead of multiplying. But again, I can rewrite this as the log base 2 of 2 to the 4th divided by 2 cubed. And you'll recall that when we're dividing powers with the same base, we can subtract the exponents. So that'll give me log base 2 of 2 to the exponent 1. Bases are both 2, so the value of this logarithm is 1. For number 9, well, now I'm subtracting logarithms. In number 8, I was dividing powers. Here I'm subtracting exponents. So we would expect to get the same answer as we have in question 8. And let's see what happens. So here again, we'll have 2 to the 4th. And here I'll have my 8 is the same as 2 cubed. Log base 2 of 2 to the 4th is the exponent, which is 4. Log base 2 of 2 cubed is the exponent, which is 3. 4 minus 3 is 1. And there we have an example of the second law of logarithms. Question number 10 and 11, a little bit different. In number 10, I have this number multiplied to the logarithm. So I'll just do times the log base 2 of 2 to the 4th. And again, log base 2 of 2 to the 4th, as we've seen multiple times already, is equal to 4. 8 times 4, 32. Number 11, log base 2, 16 is the same as 2 to the 4th, but this 16 was all raised to the exponent 8. And here I'm seeing that same multiplication as I had in number 10, where in number 10 I got to a point where I had 8 times 4. Here again, because I have a power raised to an exponent, I can multiply these two exponents and I get an 8 times 4. So I will have log base 2 of 2 to the exponent 32. Bases are the same, so the value of this logarithm is the value of the exponent, which is 32. So what's happening? What's happening here, we could see easily. We had a power raised to an exponent, so we multiplied the exponents. Over here in question number 10, remember this logarithm is an exponent. So if this logarithm is an exponent, that means this 8, which is being multiplied to it, is also an exponent. So here I'm multiplying the exponents, the 8 times the 4. Well, let's write out these rules. The first rule, if I'm taking the logarithm, and I didn't put a base in here, but we could have any base. So here I've done it with the common logarithm base 10, but it's true no matter what the base is. If I'm multiplying two arguments inside the logarithm, it means I'm multiplying two powers. That happens when I'm adding the exponents. Remember, this logarithm is an exponent, this logarithm is an exponent. So we saw that demonstrated in questions 6 and 7. In questions 8 and 9, we saw that when we're dividing these two powers, then we subtract the exponents. And then thirdly, if I have a power raised to an exponent, it means I can multiply the exponents. So this exponent of n that was written superscripted here, I can write in front and then multiply it to the logarithm, which is also an exponent. Here's how we make use of these laws. We want to simplify and then evaluate each of these logarithmic expressions. So simplifying would mean that we want to write it as a single logarithm and then evaluate to see what it's equal to. Here I'm adding two logarithms base 2. Well, I look up here, when I'm adding two logarithms with the same base, I can multiply the arguments. So this 5 and the 6.4, I can multiply together. When I do that multiplication, I get a 32, which is a power base 2, and I can rewrite that as a power base 2. I get 2 to the 5th. My logarithm tells me the value of the exponent, which is 5. Number 13. Now we're subtracting logarithms. So that would be the second law up here. On the right-hand side, I'm subtracting logarithms. That's subtracting exponents. That happens when I'm dividing these powers, these arguments that are inside the logarithm. So I'll divide the 100 by 4. That we can evaluate to get a 25, which is a power base 5, 5 squared. And so that exponent of 2 ends up being my answer. Now up here, I should probably just make a quick correction. I noticed in that first law, I didn't write in a base, but in the second law, I did put a base of a. So I should really have a base of a written here and there on the right-hand side, and a log base a written here for this third one. Maybe I'll do that for this first law as well, just to show that all three of these laws of logarithms apply no matter what the base is. And we'll move on to number 14. In number 14, we see an example of that third law, where I have a power raised to an exponent. So this exponent of 5, I can write in front of the logarithm and multiply to the logarithm. So that's what I've done here. I've brought the 5 down in front, and it's being multiplied to the logarithm. 27 is a power base 3. It's 3 cubed. And so the value of this logarithm is the value of the exponent. And so I get a 5 times 3, which is 15, as my final answer. Number 15. Now we're getting a little bit more complicated because we are subtracting, but we have this extra number that's multiplied in front of this logarithm. So we have to think order of operations. So I need to take care of this multiplication before I can do the subtraction. The way I take care of this multiplication is by bringing this 3 into the exponent of the 2. So that needs to be my first step before I can deal with that subtraction of the two logarithms. Once I have the log of something subtract the log of something, both having the same base, then I can divide those two arguments. First, I rewrote that 2 cubed as an 8, and then I can do 40 divided by 8 inside a single log base 5. 40 divided by 8 is 5. That invisible exponent is a 1. There we go. And so 1 is our final answer. On to number 16. This one is even more complex yet. We have a few stages we need to go through to simplify it. Again, I have a number here that's multiplied to the logarithm, so I need to take care of that multiplication first. So I'm going to do that, but I'm also going to change this so it's not a fraction anymore. So I'm going to change that 1 over x to an x to the negative 1, and then you can see that this 3 I brought to the exponent with the x. So now wherever I'm subtracting this argument of x cubed, because of this subtraction, that tells me the x cubed needs to go in the denominator. Because here I have addition, that tells me this x to the negative 1 needs to go into the numerator, unless I take that negative 1 down in front first. So that's what I'm going to do this time. I'm going to take the negative 1 down in front. And when I do, this is what my expression will look like. So now, since I'm subtracting both the log x cubed and the log x, this x cubed and this x will go in the denominator of our single logarithm. And then we simplify. We'll get an x to the fourth in the numerator, x to the fourth in the denominator. Well, that's, again, if I'm dividing powers, I subtract the exponents. 4 minus 4 is 0, so that's where I get a 0 in the exponent. Anything to the exponent 0 is equal to 1. Now, it's probably easier for us to go from this point to our final answer because I can see, well, actually maybe not, because here this is a base of 10, and this base of 10 is not the same as the base of x. But here where I look at this base of 10, I could say, well, this 1 is the same as 10 to the 0. So I could say I have the log of 10 to the 0, and that's going to equal 0. Well, for this question, there's more than one way we could have done it because we have these powers of x inside each of these logarithms. So what I could have done is, instead of taking things from in front of the logarithm and bringing them into the exponent, I could have brought this exponent and brought it down in front. So that's where this 4 comes from. And then similarly, I used this idea from over here where I had the x to the negative 1, and then I brought that negative 1 down in front. I've done that here as well. So that's where this negative comes from. So then if I have 4 log x's and I subtract 3 log x's, well, that gives me 1 log x. Minus another log x gives me 0 as my final answer. So this way was actually a little bit quicker. We can only do this when our logarithms all turn out to be identical. I have a log x, a log x, a log x. If I had a log x, log y, log z, I couldn't have used this method. I would have to do what we have on the blue. Well, as we look to the next page, you will find some check your understanding questions. So at this point, I'll encourage you to pause the video, work through questions 17, 18, 19, 20, and 21. And once you've finished all of those questions, restart the video to compare your answers to mine. Well, as you can see for number 17, I got an answer of 3. Again, because we are adding two logarithms, it means we can multiply the 2 powers, giving us 27. And again, similar to a question we had on the previous page, we get 3 as our final answer. For question 18, we're subtracting exponents, which means we divide the powers inside a single logarithm. That gives us a 16. 16 is 2 to the fourth. Log base 2 of 2 to the fourth is equal to 4. Number 19, we have a few steps to go through. I did this one the way we did in black for the previous question, where I kept the numbers in front, but I took this 2 and I multiplied the 2 in front here. So the 2 times 3 gave me a 6. So that's where this 6 came from. And then, because I had a log x and a log x and a log x, I could say 5 plus 6 log x's is 11 log x's. If I subtract 4 away from that, I end up with 7 log x's. Or we could bring the 7 into the exponent again and write our simplified expression as the log of x to the exponent of 7. Number 20 will be similar, but because we have both c's and d's, we can't do it exactly the same as number 19. So this time I did take the number from the front and I brought it into the exponent, and this one into the exponent as well. So then, because this is a positive in front of this log c squared, that's why this c squared is in the numerator. We have a positive or addition in front of the log d squared, so that's why this d squared is also in the numerator. Because we have a negative in front of this log c to the fourth, this c to the fourth ends up in the denominator. But then we can simplify because we have a c squared and a c to the fourth. Since we have the c to the fourth in the denominator, when we reduce, I could just think of this as being a c squared times c squared. The c squareds cancel out and I'm left with a c squared in the denominator, and here is my final answer. On to number 21. Well, as you looked through the work, hopefully you observed that Emma did everything correctly. No mistakes in her work. We can just follow the process all the way through. So let's do a quick look at it. This 8 rewritten as 2 cubed is correct. That 3 brought down from the exponent and multiplied in the front. And then if I have 4 log base x of 2, and I subtract 3 log base x of 2, because these two logarithms are identical, it's kind of like they're like terms, then I can just subtract the coefficients. So it's kind of like if I had a 4a minus a 3a, as long as these two variables are exactly the same, no matter how complex it looks, log base x of 2, I can still just subtract those coefficients to give me a 1a, or in this case, a 1 log base x of 2. Shane's work has a mistake in it though. It's mostly good, but Shane had a problem once he got to his last step. So what Shane did was, here we're subtracting logarithms, which means we should be dividing these two arguments. So 16 divided by 8, so that's what I showed down here in the red. Instead, what Shane did was he subtracted the 8 from the 16, which gave him an incorrect answer. And then finally, Clayton's mistake was pretty close to the top. Clayton took this 4 times the log base x of 2, and he multiplied the 4 times the 2 instead of bringing that 4 into the exponent. Shane did it correctly where he brought the 4 into the exponent here, but Clayton did not. So that's where Clayton made a mistake. So if we were to summarize the mistake in words for each of Shane and Clayton, well, first we could say that Emma's work is correct. Shane subtracted instead of dividing the 16 and the 8. Subtracting 16 minus 8 should have divided. And Clayton multiplied 4 times 2 instead of writing 2 to the exponent 4, which is what Shane did. And there you have the end of this lesson. So here are some practice questions for you to work on from the textbook, and then I'll see you again in the next lesson.